Okay, today we are learning a method called U-substitution. U-substitution is kind of like the reverse of the chain rule. When you had to find a derivative using chain rule, you have to integrate it using a method called U-substitution. Some people call this the chain rule for integrals, but to me it's always been U-substitution, and that's what I'll always refer to it as. So, and to me it's the reverse of the chain rule. So when you differentiate a function using chain rule, you say we had to differentiate. Let's just do sine 3x for a second. Don't write this down. Just watch for a moment. So if I had y equals sine 3x, and remember chain rule applies whenever you have what's called a composition of functions. It means you're plugging one function into another function. And a way to think about it is if your argument is anything other than just x, you have to use chain rule. So if I were to find y prime, it would be cosine 3x times 3, right? You have to multiply by the derivative of the argument. So to undo these kinds of derivatives, we're actually looking in the problem to see if we have an argument and its derivatives somewhere in there. Remember when you use chain rule, the argument always stays the same, right? So what we're going to be focusing on for the vast majority of these problems is the argument of the function, and we're going to call that u, because we don't know how to integrate when the argument isn't just x. So we have this method for doing it. So here's what we're going to do. We're going to take the argument, the 3x, and we're going to rename it, and we're going to call it the letter u. U is not a variable. It's technically the name of a function. But we're going to treat it like a variable, kind of like y. Y usually represents a function, but we can treat it like a variable. So we're going to do the same thing with u. So I'm going to let u be the argument, which is 3x.
I don't want to be the argument.
Oh, I'm sorry. Now, the nice thing about it is if we were to rewrite this then, we'd have sine u, and then we could integrate it, right? Oh my goodness. Okay. So I'm going to do this a little differently from how I did first period. So first I'm just going to rewrite this a little bit. So instead of sine 3x, we now have the sine of u. But we have a problem. Your variable and your differential have to match. We can't have sine u and then dx, right? We can't have a u here and then integrate with respect to x. That would make no sense. So we've got to have a du there. How are we going to get a du there? You can't just pull the dx out and stick a du in and hope for the best. So we have to actually calculate what du needs to equal. So here's what we do. We go back to where u equals 3x, and we're going to take the derivative of both sides. So the derivative of u would be du dx. And the derivative of 3, or 3x, is 3. Now if you remember from those differential equations we did, we can treat this like a fraction and multiply both sides by dx. So what we get is du equals 3 dx. Now I will tell you, once we're done with this example, I'm not going to write this middle step anymore. I'm going to go straight from here to here. And I want you to get in the habit of saying, all right, the derivative of u is du, the derivative of 3x is 3 dx. So you're going to multiply whatever your derivative is by dx. It'll just save you some time because we're going to do a lot of these. Alright, but if I look at my problem, I don't have a 3 dx, I just have a dx. So what I need to do then is solve for dx. So I'm going to divide both sides by 3. So dx is actually equal to 1/3 du. And I can replace the dx with 1/3 du. Now personally, I like to put the coefficients in front, so I'm going to put the 1/3 over here. You could even put it in front of the integral symbol, and then put the du over here. Now we can take the integral of this. So this is a function where we look at it, we know the answer, so we have 1/3 times. What is the antiderivative of sine u?
Negative cosine.
Very good. It's negative cosine u. So we get negative cosine u plus c. If the problem is presented with a variable of x, the answer has to be in terms of x.
So do we put in 3x?
So now we've got to go back and replace the u with a 3x.
So for U-substitution, can you only use that with trig functions? Or
Good question. We're going to do it with all kinds of
So you can
functions.
do it with like natural log functions. Then.
But you do it. You're going to be using U-substitution from today right through May. Probably almost every single day.
That sounds like...
It's kind of like how often do you use chain rule? Practically every derivative you do. All right. Now, just to check it, and you don't have to write this down, but I'm just going to show you, just so you understand what's going on. Suppose I started with this, and I just wanted to check to make sure this worked. If I found the derivative, so let's see, I'd have negative 1/3 times, what's the derivative of cosine?
Sine.
Negative sine. So I get negative sine 3x times 3. And what happens is the 1/3 and the 3 cancel, and the negative cancel, and I end up with sine 3x. Oh, look at that, it's what I started with. Right?
Go you.
Okay, so it worked.
You get it? Go you.
Go you. You know what? The hardest part of U-substitution is finding u, right? So that's the challenge, is learning how to find u. We're going to seek you out.
It's like looking into
Really?
yourself.
Yes.
Really?
There's no I in team.
Actually, it's in
Nine.
middle VA.
There's an I in 10.
There's an I in window.
People are I.
There's an I in indigo. Elephant.
Elephant.
Indigo. Igloo. Eskimo.
All right.
Aborigine. All have eyes in them.
What I want you to do first,
See?
take a look at this and just see if you can figure out what u and what du are. Just try it. Take a guess. I will tell you, u is almost always going to be in parentheses or in a denominator. Not 100%, but very, very often. Way more often than not. What's your u? 2x cubed. U is 2x cubed. Usually, u is the argument of the function. Not always, but often. And you want to look to make sure you have the derivative. Because when you did chain rule to do the derivative, you always multiply by the derivative of the argument. So you kind of want to look, u would be that original function, and you just kind of want to take a gander and make sure that its derivative is there. If the coefficient is wrong, that's okay. Coefficients we can clean up. But if there's an x cubed, you want to make sure there's an x squared somewhere. All right? So here we go. Our u is 2x cubed. Did everyone get that? So du would equal what?
6x squared.
6x squared dx. Now, there are several teachers in this school that teach AP Calculus, as you know.
3.
Right? Okay, yes.
A few.
To be
I think a
exact.
few is the correct.
Several and is different from a few? What does several mean?
A couple is
More than
2.
four.
A few is 3.
Several
and
is more
several
than
is more than
4.
4 or more. 5 or more. That's
Sorry to ruin your entire
What's four
existence,
more?
but the answer is a few teachers that teach AP
That's three.
Calculus.
So anyway,
3 or 4 is a few.
we have different approaches on how we handle what to do from here. I'm going to show you both approaches, and I'm going to let you do whatever you prefer. But I will tell you, once I show you both, I'm just going to do the one that I always do because that's my approach and that's my comfort.
I prefer math.
So, alright, so I am going to show you my approach, and then I'm going to show you an alternate approach, but I will tell you for all the rest of the examples for the rest of the year, I'm going to use my way, okay? So, here we go. First thing that we do is we are going to replace, so I'm going to leave a little space, I'm going to replace the 2x cubed with u. Alright, so now this function is good. It's all in terms of u. Then I look at what I have left. What I have left is x squared dx.
Oh, snap.
I need to figure out what to replace x squared dx with. So I look at what I've got and I say, well I have 6x squared dx. I could just divide both sides by 6. And now, hey, look at that. X squared dx is equal to 1/6 du. So I'm going to replace my x squared dx with 1/6 du because this equals this. Alright, now I've got the entire function completely represented and it's all in terms of u, so now I can anti-differentiate. Anyone know what the antiderivative of secant squared u is? Tangent u, right? So, and then of course I go back and replace the u with the 2x cubed. And there's my answer. The alternate method that for doing this, which I'm just going to show you once, alright, so the alternate method for doing this is backing up. So pretend that we were here, where we left off. The alternate method is to always solve for dx. Ignore everything else. Just solve for dx. So we have 1 over 6x squared du equals dx. So no matter, you don't even look at what you got, you just solve for dx. And then you just replace. So the x squared just comes along. I have secant squared, the 2x cubed is u, and then dx is 1 over 6x squared du. And now I can cancel. So I cancel my x squareds, and now I just check to make sure there's no x's in the problem, and there aren't. I have a secant squared u, and a 1/6, and a du. And now if you want to write it cleaned up, just for visual, you don't have to, but, and then you just go to the answer from there, right? So every teacher has, a comfort with whatever it is that they've always used. And so this is another teacher's method. It's totally fine, works great. And if that's makes you happy, you go with it.
Which teacher?
A teacher.
Yeah.
Alright, moving on. Does it matter?
Yes.
Yes.
Why would it matter?
Because
Because on Yang's chest review, he does some work, and then, you'll see, if he does it that way. You'll be like,
Yeah.
oh, why am I so confused?
Is it Mr. Yang or is it Mr. Jones?
Actually, I honestly,
I think they both do it and you're the outlier.
I don't know. I don't know what Mr. Jones does.
But Mr. Yang does it that way.
Mr. Yang does that way.
I bet Mr. Jones just like thinks the answer and it just appears.
It just appears.
I bet he does it all in his head and he doesn't know how he does it.
He just magics it.
Uh-huh. Okay. Let's move away from trig for a little bit.
Oh.
Now, look at this problem. If I just presented you with this problem, would you even need U-substitution?
No.
Why not? What could you do?
Distribute the x and
Yeah.
then just take the.
Yeah, you just distribute the x, right? And you just have x cubed plus x, you just take the antiderivative, right? So what makes us use U-substitution? Well, that would be if I did something like that, right?
That's just kind of
Okay?
Just do it out.
Yeah.
You want me to go ahead and just distribute that whole thing to the 15th power and then distribute in the
Yeah,
x.
don't be a baby.
What's wrong with that?
Come on, don't be a baby.
It wouldn't take that long. Do a little binomial expansion, right? Or do a simple U substitution. So I want you guys to try this. Come up with your U, find your du, and see if you can replace what's in there with what you get. We're just missing Morgan, right? Curtis? Yes.
Sadly.
All right, what'd you get for U?
X squared plus
What's du?
2x dx.
2x dx. Now what I do is, I know this is going to be u, right? By the way, did you notice we didn't make u equal x squared plus 1 to the 15th? U is just the argument. It's not the whole thing. It's just the argument. It's usually the stuff inside the parentheses. So we now have u to the 15th, so what's left is this x dx. So I look down here and I got x dx, but I got this 2, so I'm going to get rid of the 2. So now I'm going to replace. So this becomes u to the 15th, and x dx equals 1/2 du. So I replace my x dx with 1/2 du. And now I can just anti-differentiate. So I get 1/2 times, so the integral of u to the 15th would be 1/16 u to the 16th plus c, or 1/32 times, what do I have to do?
X squared plus.
I've got to replace the u back with x's, x squared plus 1 to the 16th plus c. You don't leave u in your answer. Always go back to x's. Okie dokie, let's do one more like that.
Why is it 1 to the 1/16?
Raise the power by 1, divide by the power.
Oh, I gotcha.
Okay. Alright, this is very similar to the one you just did. Alright, one more of these, then we're going to move into some special cases.
Hey, can I go get my lunch?
Is your lunch like at the main office or something?
Yeah.
Yeah, that's okay.
Thanks.
Just practice that x is the third or the 500.
This is a good question. That's x cubed. This is x cubed times the square root of 5 minus x to the 4th. So the 3 is on the x here, not in the, it's not the index of the radical. X cubed.
Can U-substitution get really mean?
Can U-substitution get really what?
Mean.
Mean? Yes. Absolutely. And it will never go away. You'll get to a point where you'll love the antiderivatives that don't require U-substitution because almost all of them from today forward will. People always wait till I walk over to pick up their pencils. You don't want to mess up and have to erase.
Like so.
Yeah, it's got a latest problem.
I have.
What's your U?
5 minus x to the 4th to the 1/2.
Ooh. Is it 5 minus x to the 4th all raised to the 1/2?
No.
It's just the argument, 5 minus x to the 4th.
Oh,
Okay? Guys, let the U just be the argument, not, don't raise it to a power. Does that make life easier?
Yeah.
Yes.
I quit.
You quit? Now is not the time to quit.
Sorry.
Just wait till they get really hard, then you can think about that. Okay.
It's too late to take A and B.
Alright, du. It's a little too late to switch. Negative 4x cubed dx.
Yeah. A lot easier when you got extra root.
I got ice cream for lunch.
Do you really?
I prefer frozen yogurt.
I prefer a nobody cares.
Oh.
Don't be dissing my vanilla ice cream.
Oh, you got Haagen-Dazs. That's good.
It's
Alright.
expensive though. Hot sauce is expensive.
Alright, so we're going to replace this with u to the 1/2. And we need an x cubed dx, right? So I'm going to solve x cubed dx. I'm going to divide that negative 4 out. So negative 1/4 du equals x cubed dx. So I can replace the x cubed dx with a negative 1/4 du. And now it's just a normal integral. So we have negative 1/4 times, this would be 2/3 u to the 3/2, oops, 2/3 u to the 3/2 plus c, and you end up with the 2 and the 4, so negative 1/6 times the square root 5 minus x to the 4th cubed plus c. And if you left it in exponential notation instead of radical form, that's probably just fine. All right, there are some special cases we need to learn. U-substitution isn't always this easy and straightforward.
Well, I mean, it's a big bag. I have quite a bit of stuff. We tried some wings.
Haagen-Dazs is way too expensive. They're so good.
The best ice cream by far is Ben & Jerry's.
Yeah, like I just said that.
Like I can get a 1.5 quart ice cream for the same price that those tiny Haagen-Dazs things.
I went to Ben & Jerry's. Have you been to Vermont?
Yeah, no.
Oh, really?
No.
I got to, it was really fun to tour there.
The Ben & Jerry's
They
like,
have so many different
Yeah.
flavors, like a little.
can't you buy that traveling plant thing?
Their actual factory?
Yeah, that's what
I like the,
Oh, it's a traveling?
No, not I just misspoke.
Oh,
Did you know that the
yes,
guy
yes.
who is the taste tester for Ben & Jerry's, they have his taste buds insured for $1 million? And did you know that he tastes with a golden spoon so that the like corrosive elements in the spoon don't like affect his taste? Like they were originally gonna produce this peach flavored ice cream, and they had bought a bunch of like peach land in like Georgia. But then what happened is there was like a terrible I think a hurricane, and it wiped out all the peaches. So they used one of his backup recipes. Guess what his backup recipe was? Oreo ice cream. Now one of the most successful flavors of ice cream in the world.
Good to know.
Ben & Jerry's is like my favorite ever.
Okay, so here we go. Taking a look at this one, tell me this. What does your gut tell you you should be?
X plus 3.
And it is x plus 3. So,
I don't
good.
believe you when you say it.
Good, you got a good gut.
She's gonna make us erase everything.
I'm not.
Okay.
We're not going to erase a thing.
Okay.
Can't solve for X.
Okay.
Watch it go 5 or 2X like pop out of nowhere.
So, what's your du?
DX.
dx.
Isn't that just marvelous?
Alright, let's take a look at this function now and see what we can replace, right? So this becomes u to the 1/2. You know what, I'm going to put the space on the right hand side. So this becomes u to the 1/2. So I got that done, right? This is gone. I'm just going to underline what's taken care of. So that's gone. dx, well, we know what that is. dx is du. I still have an x unaccounted for.
Well, that's a pain.
It is, isn't it? Now, when I have an x unaccounted for, the number one thing that you are never ever allowed to do ever, under severe consequences, is put the x out front and then just pretend it's not there and do the integral and then multiply it in at the end. Okay? Never, ever, ever do that. You are not allowed to put a variable in front of an integral symbol, only coefficients, right?
That seems so clever though.
Yes, and yet it's dead wrong. All right. So we've got to take care of this x. Remember, the whole goal is just to write all of this in terms of u. So is there a way that we could write x in terms of u? Yes. So you look at our original equation and we say, well, let's see. If u equals x plus 3, then x equals u minus 3. And I can just replace the x with a u minus 3.
Oh.
That's some pretty slick algebra
Okay.
right there.
Now, in order to integrate, what am I going to have to do first? I'm going to have to multiply this out. What's u times u to the 1/2?
U to the 3/2.
U to the 3/2 minus 3u to the 1/2 du. Everyone always feels like when they get this far, they've like worked so hard that they should be done, and then they just plug the x's back in, but we haven't actually found the antiderivative yet, right?
Oh.
Okay, so we still have to antidifferentiate. So this one would be 2/5 u to the 5/2 minus 3 times 2/3 u to the 3/2 plus c. And what's the last thing we have to do? Replace our u's with x plus 3's. I need to warn you that your book on these problems, if you look at the answer key, they're going to pull a GCF out of every term and then clean up what's left. You don't have to do that. You can leave it just like this. This, to me, is a happy answer. They're going to pull an x plus 3 to the 3/2 out of both terms and then write out what's left. Just warning you when you check. All right? Okay, wait, I don't know why I'm hearing clicking sounds. We're not done. Okay, suppose, backing up. Okay. All right. My last example I'm making up on the fly because I did not like my example this morning. So I'm going to do something that is just like what we just did. But I'm going to give it a kick. And we'll see if this works. If it doesn't work, don't watch any further, but if it does work, then keep watching the video.
Well, how would they know?
I know, they won't. So, all right, here we go. What's u? X minus 2. So du is, again, dx. we go through, we write our function, so we have u to the 10th, and dx is du, but what's unaccounted for?
X squared.
X squared.
U minus
Oh.
2 squared.
Well, so we know x equals,
U minus 2.
close, u plus 2,
Oh, yeah.
right? We want x squared, so we've got u plus 2 squared. We don't know how to integrate this. We got to square it out. So this is u squared plus 4u plus 4. That goes in here. And you'd still have to distribute in order to integrate. All right, guys, homework tonight is 4, 5. Remember that tomorrow